We prepared a hands-on tutorial for you. This tutorial is prepared by Karsten Einwich from Fraunhofer, Torsten Mähne and François Pêcheux from the University, Pierre and Marie Curie. And I'm Barnasconi from NXP Semiconductors. So we're going to show you in this tutorial what you can all do looking at waves. We didn't do checkers, but this is not verification, right? So it's allowed to look at waves using SystemC AMS 2.0. What's on the program? I have a short intro before we go into session 1. I give you a bit of history, the objectives of SystemC AMS, we position it a bit, and then I dive into the tutorials themselves. Here you see the overview of SystemC and SystemC AMS, so SystemC at the left side, which started more than 10 years ago. And actually, if you look at the right side, even the first extensions for SystemC AMS were already developed long time ago, resulting in proof of concept implementation somewhere around 2005, 2006. So, is this new? No, not really. The technology is rather old and as such also very stable. And what is nice to mention here is that we are also preparing the Dan-1 Accelera will move into IEEE. So there will be an IEEE P1666.1 formed, which will be the starting point of the creation of an IEEE standard. What are the objectives of SystemC AMS? At the end, like SystemC, we are targeting system level design, but then for mixed signal. There are other languages out there like Verilog AMS and System Verilog, which are much more addressing the verification and implementation domain. With SystemC AMS, we're really addressing the system level modeling domain. We would like to create architectural designs and do architectural exploration using SystemC AMS. And as this is based on C++, it also facilitates a good platform for model exchange. So not only for digital, but now also for AMS. We built this on SystemC, so we can facilitate a seamless interoperability with known ESL design methodologies. So hardware-software descriptions you normally have with processors can now be extended with analog mixed signal extensions. And I think what we have done as well is we have made some dedicated models of computation which are very efficient at the system level. So new abstraction methods and concepts will be introduced. So if you position that in a graphical way, you see something like this, is that we have at the implementation level the known HDL languages. SystemC is more for the architecture domain and SystemC AMS complements the domain where we can do architectural design. So the tutorial overview, so what we will do, we have split this into 3 sections. So the first section is a very introduction section where we give the foundation of SystemC AMS and we are going to conduct the first lab, and I encourage you all to grab your laptop and let's work together to create a very simple analog case, which is in this case a sinusoidal source, and get the first waveform on the screen. The second session, we dive into different models of computation. So we will look at AC domain, we look at signal flow domain and electrical domain. And the lab there is that we are going to extend that simple example, doing some analog filtering, and we are going to introduce sigma delta ADC. And then session 3 is the more advanced stuff. So we are going to look at the extensions introduced in SystemC AMS 2.0. And as a bit of a system example, we will look at a vibration sensor. So for the labs, the links are listed here. We are using a tool from Fraunhofer called CoSite, which is a system-level design environment, including a graphical user interface and a way to including simulator. The examples are in labs, in a file called DVCon Labs Workspace, WS, and we also have some startups. That concludes the introduction. I would like to hand over to Karsten for the basic introduction of SystemC AMS.
I'm honored to present the basics of SystemC AMS, the basic concepts, the basic structure. The outline is I will talk about the SystemC AMS language composition, the models of computation. The most important model of computation in SystemC AMS is the so-called time data flow domain. And then we have also 2 other domains. And then I will give a short overview what kind of simulation and control and debugging features we have included in SystemC AMS. And after this first session, we will have the first very simple lab. A SystemC AMS language composition. Now, what's different between analog and digital? If you look to SystemC is all models of computations are mapped to the synchronization of different processes. And if you look to analog, you cannot easily map such analog behavior to this generic model of computation. In analog, usually you have to set up equations. You have to use the modules, the components, and to analyze or set up an equation system from it. And it's usually an implicit equation system. That means the most important difference is that you cannot map analog behavior in the general case to the communication of processes. And the second thing is that the analog state is changing continuously. That means the value between two calculation points is continuous and not discrete like in the digital domain. And this has one consequence, especially for system level. If you have different time scales, it's not so easy to synchronize these two time scales, because if you want to have a value between two calculation points, then you have to interpolate. And interpolation means usually you need the point in the future. The other thing is you can synchronize all calculation time points, but this always slow down your performance. How SystemC AMS represents analog modules. And what I mentioned before, in AMS, behavior cannot map to the communication between different modules and processes. That means in analog, the modules themselves have a special meaning. That's why we have in SystemC AMS, each model of computation has its own primitive modules. That means the primitive modules for one model of computation must be derived from a specific base class. And also for the connection between modules, it's not like in SystemC where this is our communication channel. In SystemC AMS, usually in the general case, a connection represents a variable in the equation system. Nevertheless, all SystemC AMS language elements, that means the modules and also the channels, the connections, are derived from the SystemC base classes. On this way, we have the same behavior for connecting modules and for building hierarchy of modules. But if you compose system in a hierarchical way, then we use the same methods like we have in SystemC. That means we have to create SC modules with a SystemC constructor, and we have to instantiate and bind the modules same way like in SystemC. Now, what I mentioned before, we have three modules of computation in SystemC AMS. The most abstract model of computation is the so-called time data flow model of computation. Then we have a linear signal flow model of computation and one conservative model of computation, the so-called electrical linear network model of computation. We always recommend as far as possible to use this time data flow domain. Similar like in SystemC, we have some naming conventions. All symbols which are in the SCA standard are prefixed by SCA underscore. That means you as a user should never use such a prefix, because then you are dangerous that you get some symbol collapse. Also, like in SystemC, all symbols are embedded in a namespace. With this concept, we realize extensibility, and we have different namespaces for the different models of computation. That is the difference to SystemC. That means we have three namespaces. One is called SCA TDF, SCA LSF for linear signal flow, and SCA ELN for electrical linear networks. And then we have two general namespaces, SCA core for core elements, which belongs to a special namespace, and utility, SCA util for utility functions like tracing, special data types, and so on. And one namespace, which is for the special analysis, SCAC analysis, which we support in SystemC AMS. And if you are looking to the basic keywords, we have SCA module as base class for SystemC AMS primitive modules. We have SCIN and SCA out ports for non-conservative, that means they're directed ports. We have SCA terminals for conservative ports, that means maybe an electrical port. We have SCA signal for non-conservative directed signals, and we have SCA node and the special node SCA node reference for the reference node for conservative connections. If you look then in the concrete case, that means the TDF module has the naming SCA TDF SCA module. And this is an example for an LSF import because it's a directed port, SCA LSF SCA in. And for the data flow domain, SCA TDF SCA in, because it's also a directed port. And in the data flow domain, we can have arbitrary data types. And for the electrical domain, terminal SCE, ELN, SCA terminal, and the corresponding node is an SCEL and SCA node. And then we have in the language some elements which converting between different domains. And there we have also naming conventions. In this case, we have a port which is able to convert in discrete even, that means in system C, classical system C signal to the TDF domain. That means this is a port in the TDF domain coming from the discrete even domain, and it's an input of an arbitrary type. And similar, we have then for the electrical domain, there we have special elements like voltage sources or voltage sinks. In this case, it's a voltage source in the electrical domain, which converts the voltage from a TDF input signal. Similar, we have then for the linear signal flow domain, where we have a linear signal flow element, which converts a system C signal to an output signal. What I mentioned before, the data flow engine is for abstract modeling one of the most important engines. Data flow is a very simple model of computation. It has a very simple firing rule. Data flow means a module can be activated if enough samples are available at the input. And for static data flow, what we are using, or synchronous data flow, this number of samples is known in advance. A function of the module is executed, it reads from the input, processes the calculation, and then it writes the sample to the output. In this case, if you see this simple cluster, then this module is activated, produces a sample at this output, then this F1 can be activated, produces a sample at the output, and then F2 can be activated. This way, the scheduling always follows the signal direction, and this is why we can use this also for analog modeling, because for analog modeling, abstract modeling, you need exactly this to solve the analog equation system. There's one issue with loops. If you look to such a data flow graph, then you see this graph cannot be scheduled with this firing rule, because this adder module, in this case, there will be never a sample so that it can be start to schedule. In the data flow domain, you have to introduce delays in such loops. A delay in the data flow sense means that in the initialization phase, the sample is added. And if here's a sample available, then again, this module in can be executed, the adder can be executed, F1 can then be executed, then F2, and then a new sample is produced here, and the scheduling can start from the beginning again. That means this is one restriction we have if we are using the data flow modeling domain. If we have loops, then we need a delay in the loop. That means we cannot solve, in this case, algebraic loops. SystemC AMS supports also multi-rate data flow. Multi-rate means that the rates are different from one. That means the number of samples which are produced or consumed. In this case, we have a source which produces per execution one sample. We have this module B, which consumes 2 samples per execution and produces 3 samples, and module C, which consumes 1 sample per execution. And the resulting scheduling order is then, okay, first we have to activate 2 times module A, then we have 2 samples available, can activate module B, producing 3 samples, and then we can activate 3 times module C. The data flow we have in SystemC, the special thing is that we have so-called timed data flow. That means we're doing a timing annotation to the sample. For SystemC AMS 1.0, this annotation was very simple. We defined at one point in the data flow cluster the time distance between 2 samples. And then we were able to propagate this through the whole systems. And on this way, we have a timing annotation inside the data flow domain, and also for synchronizing discrete even signals with the data flow domain. So this timing annotation is important to model analog behavior, because analog has always to do with the time. One example, in this case, we have a simple data flow cluster. We have assigned one time step of 10 microseconds to this port. That means we define the sample distance between 2 samples at this port is 10 microseconds, and the rate of this port is 4. That means the time step of the module is 40 microseconds, because we have to produce 4 samples per module execution. And then we can propagate this time step through the system. The connected port is clear, must have the same time step as 10 microseconds, because this has a rate of 1. Then the module must have also a time step of 10 microseconds. And the port output has a rate of 2. That means we have to produce 2 samples per 10 microseconds. So we have 5 microseconds, and then we can propagate this to module A and also to the time step of the module. This is what we are doing in SystemC AMS. That means the user at the end defines at one point in the cluster the time step, and we propagate it through the whole cluster, and we check consistency of this time step. Summary, we have three important attributes to ports. One attribute is the rate. It defines the sampling rate. We have the delay. It defines the delay value of a port, and we have this time step. So how we synchronize between the discrete even domain and TDF domain. It's a very simple synchronization, especially for SystemC AMS 1.0. We simply sampling the discrete even signal with the time steps we have in the data flow cluster. And in the opposite side, we simply writing to the corresponding time steps to the discrete even domain. For SystemC AMS 2.0, we have then also the possibility to synchronize the data flow executions to discrete even signals, so we can become a little bit more reactive. How is data flow simulation work? We have an elaboration phase and we have a simulation phase. In the elaboration phase, we have one callback called set attributes, where we can set the attributes to ports and to the module. Then we calculate the time step and propagate the time step. Then we calculating the TDF cluster execution. And then we're starting the simulation with an initialization phase. There's a callback initialize, where you can set initial values. And then we repeatedly call a callback processing, which contains behavior of the module. And at the end of the simulation, the classical end of simulation callback of SystemC is executed. What are the language constructs for describing the module? We have this module declaration. Its structure definition is a module name derived from the SCA-TDF module base class. We have this macro for convenience. And then we have the ports, the TDF in port and the TDF out ports. And we have this converter port, TDF SC in, TDF SC out. And then we have this callback method, set attribute, initialize processing, and optional also EC processing to provide behavior for the EC simulation. This is how a module looks. We have this module declaration, SCA TDF module. We have two TDF in ports, a TDF out port of type double, that attributes callback, initialize, and processing. This is a structure of a user-defined primitive. Then we have methods for setting the attributes of ports. There is set rate, where you can set the rate of a port per default. If you do not set it, the rate is 1. And of course, we have the get rate. The same we have for delays. Per default, the delay value of a port is 0. And you have also this get function. And then you have the possibility to set the time step of the port, and get time step. If you do not set the time step of a port, then it is propagated from the cluster. And then there is also a method to get the absolute time of a sample. For writing to ports, we have different methods. For the initialization of delay values, there is a method initialize. And then we have read and write methods and corresponding operators for convenience. But usually you should use the read and write method to read and write from ports. Okay, there's a very simple example. It's maybe from an RF system, a mixer. A mixer is a simple multiplication of two analog signals. We have an RF in and a low in port of type double, and we have an output port. We're setting the time step to 1 microsecond, and we're setting the delay value of the output to 5 samples. In the initialization phase, we initialize these 5 samples with 0. And in the processing phase, we simply see the output is input 1 multiplied with the second input. What I mentioned before, hierarchical descriptions are similar like in classical SystemC. We have SC module declaration, we have the in and out ports of this hierarchical module. We have module A and B, the instances. We have internal signal, and in the constructor we have then to define this netlist. That means here we instantiate module A and connect this in 1 of module A with this in port, in 2 of module A with this out port, and this out port of this module with this internal signal. And here we instantiate module B, connecting this to this signal and connecting this output to this output. Yeah. This is a classical netlist description, like you know it also from other languages. Simulation, control and debugging. One topic is tracing of analog signals. SystemC has tracing mechanism, but in SystemC AMS we're using an own one. This has two reasons. One reason is that supported format of SystemC, the VCD format, is not very efficient for analog waves. And the second reason is that we have in SystemC AMS different time scales which must be synchronized, so that we need our own trace mechanism for AMS signals. We can trace with this SystemC AMS tracing mechanism all signals, all nodes, also nodes in the ELN domain representing the voltage of this node, and also all classical SystemC signals. And we can trace also electrical linear network elements. And if you trace an electrical linear network element, then we mean the current which is flowing through these elements. And then, of course, we can trace ports and terminals, which means the connected signals or nodes. And for internal states, we have a special trace variable which makes these internal states accessible. We support two formats. We have this tabular trace file format, and for compatibility reasons, we are also supporting the VCD trace file format. That means the digital wave format. And what's also available in SystemC AMS, that means we have different features to reduce the amount of data, because we have seen simulation is so fast that we can produce so much data that it becomes very hard to analyze them in wave viewers. And sometimes the writing of the data dominates the simulation performance. So we introduce some functions to optimize the amount of data we are producing then. The tabular trace format is a very simple format. In the first line, we have the names of the signals, and then we have in the table, the first row is the time, and then the values. And this is a format you can read in a lot of waveform viewers, or you can also easily load it into MATLAB. Simulation control for time domain simulation, the same commands like in SystemC are used. The scstart command with its different versions, also the new SystemC 2.3 commands, scpause, are available. And we have additionally the AC domain simulation. There we have two flavors. One is the SCAC simulation, the classical AC simulation, and one is the SCAC noise simulation. One example for a test bench. It's the same like in SystemC. We have Mähne. Then you have to declare the signals, you instantiate your DUT, connect your DUT, you instantiate the traces. Also you can have classical SystemC traces in parallel to SystemC AMS traces. Then you can use the scstart command to start the simulation. And here we're using some of these trace file commands like to disabling the traces for a certain time. If you say, okay, I have a settling behavior, I want not to store all the samples on the settling behavior, then we can simply disable in this time the traces. It reduces the amount of data you generate and speed up maybe the simulation performance. Yeah, you start again. Then we have also some tracing command like setMode. We sample the traces. This can also be used to reduce the amount of data or be used to get the data for an FFT on the correct raster so that you can directly perform on the output data the FFT. Then here we start again the simulation for 100 milliseconds, and then we're closing the trace file.
I will continue the presentation about SystemC AMS, and I will talk about models of computation. The idea is that TDF is the privileged model of computation of SystemC AMS. There are two others named LSF and ELN. In this session 2, I will present some constructs that can be useful in TDF to model linear dynamic behavior. I will talk about linear single flow very shortly. Also, I will talk about ELN examples very shortly. And my colleague Torsten will present small signal and frequency domain analysis capabilities of SystemC AMS. So what about linear dynamic behavior in TDF? The idea is in TDF you can have one of the three following forms to model linear transfer function. You can use what is called the numerator-denominator representation for linear transfer function, like this. And in SystemC AMS, you will see there is a way to set up the B and the A coefficients of this numerator-denominator representation. You also have another representation called pole zero. That also involves setting of coefficient in a specific function of a TDF module. And if you want, you can also set up your system as a state space equations. To do that, SystemC AMS provides 3 SystemC AMS objects. They are named here. You have SEA, LTF, ND, SEA, LTF, ZP, and SES, SS for state space equations. The idea is that these objects will be instantiated in your models, and the whole computing will be done with continuous time. But thanks to the object provided in the slide, the proxy, there will be time discretization at the input and at the output of these primitives. So you can use them in the TDF context with discrete time set with the time step. This way, we have a very fast calculation in the case of multi-rate systems. So the idea to show how these objects work in SystemC AMS is to look at an example. So this example is a filter. It is a programmable filter with 2 cutoff frequencies. The first frequency is 1000 Hertz. There is a second cutoff frequency, 100,000 Hertz. And the idea is that you can switch from one cutoff frequency tier to another using this discrete event signal called FC high. So you have the input of your module, is SCA TDF SA in carrying double values. You have the output of your filter. You have what is called a converter port. Martin will talk about later in the presentation. The converter port allows the discrete event signal to control the behavior of the analog. And you have the famous constructs that are needed to build up the filters. You have 2 objects called LTF0 and LTF1 of this C++ type, SCA LTF ND. And once you have instantiated this object in your model, you are able to perform filtering. To make the object here work, you also have to define 3 vectors called A0, A1, and B that will be used to define the coefficients of the numerator-denominator of a linear transfer function. Where you define the values of these vectors in the initialize function. So if you want to build up a filter that is able to perform this kind of linear transfer function, you have to define the coefficients B0 as 1, E0 or A1 as 1. If you have 2 filters, you have to have A0 and A1. And here is the way to define this coefficient. In this initialize function, you define all the coefficients that are needed to define this numerator-denominator system. And then, in the processing function, according to the value of the Boolean discrete event input here, you will use this kind of construct to perform the filtering and the call to the linear transfer function. Here, in is the input, S is the state of the construct, and here are the denominator and the numerator of this LTF construct. So according to this value, sometimes you will do this and sometimes you will do this. This is just simple code in the processing function to limit the output value. The way you set up a filter, first you define the variables, then you initialize them in the initialize function, and then you use this kind of construct in the processing function to perform the filtering within the TDF context. After TDF, there is a second model of computation called linear signal flow. I will be very short on this. The idea is that the linear signal flow library uses predefined elements that can be used to describe any system of linear equations. What is interesting is that these LEF primitives can be connected to TDF ports. So you can embed LSF behavior within a TDF module. There are several converter modules from and to TDF and also with discrete event SystemC. There are also some primitives that allow to model switching behavior with muxes and demuxes. And these LSF models are always used in a hierarchical model. If you want to define LSF port, you will have to use this kind of construct, SCA, LSF, SCA in. If you want to have output, same thing, SCA out. And in order to connect the different primitives together to perform the function or the model you want, you will use what is called SCA signal to connect different primitives together. What are the complete list of the predefined LSF modules? You have the possibility of adding values with weighted coefficients, subtraction, multiplication, derivation, integration, delay, the possibility to have source, the possibility to also have LSF version of LTF with numerator, denominator, and zero pole. You also have the possibility to have state space equation in LSF. And you can see on the second column that we can also have some interfaces between LSF and TDF with this kind of constructs and primitives and SCSOs that belongs to LSF and TDF. Same thing for gain, mux, demux, sync. And same thing for also the discrete event. So LSF models can be integrated both in a TDF and in discrete event. An example of an LSF model, you have here an LSF model. So as it is a combination of LSF model, it has to be described in a SC module. In TDF, you had the SCA TDF module, but now, because it is not just about the connection of primitives, it is in the SC module. You have the input here, the output here, the primitives that you will use to model your behavior. So if you want to have this kind of behavior with a subtractor and a derivation device here, you will have to instantiate one SCA dot and one SCA sub. And to connect them, you will have an internal signal called SIG here, defined as LSF SCR signal. And in the constructor of your model, you will just connect the different primitives together. So if you want to have this kind of netlist, I would say, you see that on the subtractor X1 input, you will connect in. On the X2 input, you connect SIG. On the Y output of this primitive, you will connect the out signal, and same thing for the derivation construct. So a short talk about ELN. This is the third model of computation available in SystemC AMS. It is also composed of predefined elements, and this is the only model of computation of SystemC AMS that is able to keep the Kirchhoff laws in order, that can model a conservative linear behavior. Like in LSF, you can have several converter modules between ELN primitives and TDF and DE. Like this, you have TDF SCR signal and SC core SC signal. You have also the possibility to model switch, and like LSF, the ELN models are always hierarchical. So to have this conservative behavior with ELN, you need to have special kinds of ports that are called terminals, like in VHDL AMS. And you also have to have nodes, internal nodes inside your models. And you also have to have a reference, the ground, called SCA node reference. Just to see what are the primitives that are offered by the ELN model of computation, you have the linear component R, L, and C. You have all kinds of voltage source on current sources, controlled or not. You have all these constructs here. And like in LSF, you also have the possibility to interconnect your ELN devices with TDF and with DE, with this kind of primitives. This is an example of ELN circuit. Like with LSF, it is described in the SC module, and you have to set what are the in terminal and the out terminal. The in and out terminal will carry both the information about voltage and current. And here you have all the primitives you want to use in your design. Two resistors, R1 and R2, one capacitor C1, and how to connect them is done here. You just follow the traditional rules to define a netlist, and you connect the component like this. Because there is an internal node here, N1, we have to declare SCA node called N1 in the private section of the model, and you have to add also a node reference here. So be aware that if you want to model with the ELN, it is not possible to do everything. You cannot connect voltage sources in parallel or current sources in series. You should avoid having zero valued resistors. Do not define floating nodes. Do always have a path to the reference node. And you should also try to set a simulation step that is compatible with the time constants of the components you are using. Again, do not use very extreme and different values between the components in the dimension in order to find a solution to the system.
Now to the small signal frequency domain analyzers, which are also supported by SystemC AMS, besides the transient analysis you are already used to when you're using SystemC. The transient time domain simulation is driven by the SystemC kernel. So you're using the classical SC core, SC start function to simulate your AMS system for a certain period of time. In addition, what you would like to do when you're analyzing an AMS system is to drive your system through a transient simulation into a certain state, and then to analyze your signal processing chain by doing a small signal analysis. SystemC AMS offers you two kinds of small signal analysis. One is a classical AC analysis, and the other one is an AC noise analysis. For the AC analysis, SystemC AMS will calculate the solution of the linear complex equation system, which is stimulated by AC sources which have a certain amplitude and phase. And for the AC noise domain, the same linear complex equation system will be solved for each noise source contribution, and these will then be accumulated. There's a particularity that the ELN and LSF models already provide these linear equations contributions, but the TDF modules which you are writing, they don't have yet this AC behavior assigned. So that is something you will have to provide. Otherwise, they will simply contribute no solution, and so that the output values of these modules will be assumed 0. Here you can see such a signal processing chain where you have ELN modules at the input, some LSF modules, and then at the end of the chain also some TDF modules. The cluster of interconnected ELN primitives will provide an equation system for the cluster from the input to the output, so that this behavior can be accounted for. The same will hold for the LSF module. And for the TDF modules, you will have to provide the transfer functions for each of the modules. And we will see it now in a small example how you can do this. Here we have the TDF model of a digital comp filter. You can see that it produces in the set attributes callback, you can see that it consumes 64 samples at its input and for producing one sample at the output, so it also downsamples the signal. The processing member function, which produced in our first lab, the sine source, would here contain the DSP algorithm to implement the transient comp filter behavior. And in addition, we also provide an AC processing member function, which provides the transfer function in the AC domain. So the transfer function with the set operator is simply 1 minus set to the power of minus k over 1 minus z over the power minus 1 taken to the power of n. And when you look at the bottom left AC processing call, you have the function h is equal this transfer function, where the z operator to the power 2 is represented with the SCA AC z function, and the argument is simply the power. And the quotient, which is taken to the power of n, this is realized with the normal power function of the C math library. To access the complex value which is coming from the input of the module, you will have to use a special accessor function, the SCA AC function, which takes as an argument a port and will return this complex function. You can then multiply it with the transfer function, which is stored in the variable h, and to calculate the output, which is then written to the output port using, again, the SCA AC accessor function. We already saw that the transient simulation is controlled with the SC start function. Similarly, we have for the AC domain and AC noise domain simulations the SCA AC start and SCA AC noise start functions, where you provide a frequency range you would like to scan. So start frequency, end frequency, and then the number of frequency steps you would like to do. And you can select between a linear and logarithmic stepping of the frequencies. You can also provide a vector of selected frequencies where you would like to do this small signal analysis. Here we have a code snippet from a test bench for doing the AC tracing. Like for transient simulation, you can trace signals and ports of the TDF, ELN, and LSF MOG. And to this end, you will have to open an SCA trace file. This time it is very important to use a tabular trace file format because VCD trace file format does not support frequency analysis. And then you use the SCA trace function to select the signals or ports to trace. And you can start your simulation. And if you're doing mixed transient and then AC domain simulation, after each change of the analysis type, you will have to reopen a different file through your trace file handle so that you don't mix transient and frequency domain tracing results. So this is done with the reopen member function of the trace file handle, and then you can start your simulation and the results will be stored in the trace file. The trace file handle also provides certain additional parameters through the setMode function, where you can set, for example, the format of the results which are stored in the trace file. For example, you can have polar coordinates of the complex results or decimal degree representation. We will present some of the advanced features which have been added in the SystemC AMS 2.0 standard. And we will also present a number of industrial case studies which have been done over the past years using SystemC AMS. SystemC AMS 1.0 was released in 2010, and last year at a date conference we finished the second version of SystemC AMS 2.0 to address a number of limitations of the AMS 1.0 standard, especially regarding its fixed time step for the execution of the TDF, ELN, LSF models, and also the lack possibility to react to events. The new features which have been added in the SystemC AMS 2.0 standard are dynamic time steps, the changing during the course of simulation of the time steps in TDF modules, the ability to react to events, trigger calculations of TDF clusters, to enable the communication between TDF clusters running at different time steps by special declustering ports, and also the ability to change the rate and delay attributes of the TDF cluster. And finally, also an important possibility to do iterations with 0 time steps to do relaxation. So there you have to re-evaluate your equation system. These new features were motivated by a number of use cases where SystemC AMS 1.0 fell short and which were communicated to the AMS working group in form of requirements. So the need to be able to abstract the modeling of sporadically changing signals. So for example, to enable power management by switching on and off AMS subsystems, to be able to describe reactive behavior so that AMS models were able to get triggered by transactions, for example, so that there is a better integration possible with the SystemC TLM standard. The possibility to be able to capture behavior of where the frequencies and thus associated time steps change dynamically, and which is very often the case when you have to deal with clock recovery circuits and to be able to capture jitter, for example, in your clocks, in your sampling clocks, or also when you're dealing with PLLs and other systems and radios where the phase or frequency is modulated. And then for the whole domain of multi-standard software-defined radios, where you have to be able to adapt your signal processing chain to different standards, you also need to be able to change the rates and delays in your TDF model. By addressing these requirements, we did this through the form of introducing dynamic TDF as a strict superset of the existing TDF model of computation, so that also now applications in the automotive domains, which often, for example, include PWM stages or have to react to threshold crossings, where you have DSP algorithms and so on, become possible to get simulated. Also, the restriction to linear dynamic equations got a bit relaxed by the ability to be able to zero time steps iterations, so that you can also, to a certain degree, describe nonlinear dynamic systems. So on the right, you can see, for example, a PWM model with varying time steps, which will be used in the continuation of this presentation to show you the performance benefits you can achieve with dynamic TDF. Just as a reminder, data flow itself is an untimed model of computation, and we basically just tag each sample with a certain timestamp. And in SystemC AMS 1.0, the distance between these samples was constant to simplify the synchronization between SystemC, discrete event, and TDF. The time steps you assign to either a port or to a module gets propagated during the elaboration phase to all the other ports and modules which have no time step assigned. And then there's a consistency check, so that if you set the time steps at different places in your model, you can verify that these are coherent. We now allow in SystemC AMS 2.0 that time steps can change during the execution of the model. All the modules which are present in the cluster have to be able to react to this time step change, take it into account, and not just assume that the time steps are constant till eternity, like it was the case in SystemC AMS 1.0. This imposes two restrictions. First, all the modules in a cluster have to flag that they are able to deal with varying time steps. And the second is that the execution of the cluster schedule has to have finished before you can change the time steps. So you always do changes in the attributes of the TDF cluster at the end of a cluster execution, because otherwise you would not be able to guarantee the consistency of your model. The TDF mock in SystemC AMS 2.0 supports now the old static mode of execution where rates, delays, and time steps were constant, and the new dynamic mode of operation. As I said, all modules have to support this dynamic mode of operation by setting a flag, and the attributes have to be always specified before the cluster execution starts again, so that full schedule will be executed. Like during elaboration, the TDF attributes have to be set in a special callback called set attributes. The changing of the attributes will then happen in a new callback, which is called change attributes. The marking of the TDF modules happens through 4 new member functions of the TDF modules. The first one is called accept attribute changes. When you call this member functions from within a TDF module, it says, okay, I'm accepting that other modules may change TDF attributes like rate, delay, and time step. I can also say that there is no attribute changes allowed. And then this is basically a passive property that you say, okay, I'm compatible with this. But you can also say that you will actively change these attribute changes. Here is a summary of these new member functions which have been added in SystemC AMS. You have the change attributes and reinitialize callbacks, which are basically the equivalents to the already existing set attributes and initialize callbacks. But these new callbacks are called during the simulation of the model. You have the does attribute changes and does no attribute changes, which marks the module whether it will actively change anything in the TDF cluster, and the accept and reject attribute changes for whether it is able to deal with attribute changes or not. And then you have a new member function called request next activation, which enables you to become sensitive to events and to ask also for a reactivation after a certain timeout. An application example for these new features can be, for example, the DC motor control using PWM modulator. And if you would try to model this with SystemC AMS 1.0, you would need to specify a very, very small time step to have the right resolution to capture all the different width of your pulse. And if you then would look in your system, you would basically do nothing because the signal itself stays more or less constant over this time. So it could be you do a lot of unnecessary calculations, and it would be just sufficient to basically evaluate your model each time when there actually is a change happening. So once you're starting to enter into the rising edge of your pulse, once you reach the plateau point, and once you get into the falling edge, and then when you're again at the bottom of your pulse. So this you can now quite easily achieve in your TDF models by first marking in the set attributes callback the model to accept attribute changes and that it will actively change attributes, and then do the changes of the attributes in the change attributes callback. In this case, with the time step, with a call to the outset time step function, where you will say, okay, when will be there the next activation after a certain duration? And this duration variable in this example, which is used there, is actually updated at each call of processing. So by using the knowledge you have about your system, you can thus enormously improve performance of your system by reducing the number of activations per period of your model by a factor of more than 125 times. So instead of 500 activations, you would have just 4 activations per period. And this extremely helps you in the performance of your simulation. To change the attributes, you will basically use the already known set time step, set rate, and set delay functions. And to react on events and to do timeouts, you can use member functions request next activation. There's also another new member function added called set max time step, which allows you to limit the timeout to a maximum duration, because often your system blocks which need a certain time step precision to properly capture their behavior. And with set max time step, you can impose these constraints. By having added these new possibilities to dynamically change time steps in your system, the need became stronger also to be able to decouple data flow clusters, and therefore new kind of decoupling output ports have been introduced, which basically enable you to explicitly specify where you want to cut your data flow cluster into 2 and specify thus the frontiers of your data flow cluster. At these decoupling points, different strategies can be applied to interpolate the values or use a kind of sample and hold regime to do the decoupling. These decoupling ports enable you to connect static and dynamic TDF modules with each other, which use different time steps. We have to be able to do interpolation or do a sample and hold mechanism. If we do interpolation, we need always 2 samples to be able to interpolate. And therefore, you will be obliged to assign a certain delay to your output so that the port can accumulate enough state to be able to do this operation. These new decoupling ports are basically a specialization of the already existing output port. They just have distinguished from the normal output port by an additional template port argument, which is SCA cut. And then you have this choice between no cut, CT, and DT to select the kind of decoupling you would like to achieve. And according to the decoupling policy, you will have additional member functions to specify the kind of delay you have. What has been also relaxed is the constraint on time steps. In SystemC AMS 1.0, you were obliged to always advance in the time, so that the time steps were always greater than 0. Otherwise, you would not be able to ensure that the SystemC simulation would continue. Now, in SystemC AMS 2.0, we allow 0 time steps to be able to re-evaluate dynamic equation systems based on an updated internal state. This is automatically taken into account by the linear equation solver for the LTF functions, the state space equations, the LSF, and the ELN solvers. And thus, for example, it allows you to take into account when you have modulated resistors or capacitors in your ELN model, or you are changing the coefficients in your transfer functions. So you can do relaxation iterations. For example, you can thus also create an abstract model of a diode, which is a strongly nonlinear component. And in this case, if you look to the small schematic, how it is realized, you have 2 linear electrical components, a voltage source and a resistor. And these are actually controlled voltage sources and resistors. And a voltage sink will measure the voltage across the resistor and the source, communicate this to the attached TDF block, which then will take a decision on the value of the voltage source and the resistor to recreate the diode characteristic. SystemC AMS applications.
Several companies which are still working on different fields with SystemC AMS. And we have applications, or we saw applications like in XP, like in-vehicle networking, in the telecommunication area for classical plain old telephone systems, EDS systems, Wi-Fi chipsets, imaging sensors, braking systems, airbag systems, and also the automotive area, the motor control, the powertrain. Huge application area are sensor circuits. Today, a typical sensor circuit consists of a processor and some analog signal processing and the sensor element, so that you need some system level model to at least develop the embedded software. In the smart card area, because the smart cards I learned have also analog components inside, driving motor systems and power supply systems. Yeah, this is a classical example from the telecommunication area, where we as Fraunhofer started together with Infineon 10 years ago to applying analog extensions to SystemC. And there you have the typical problem. You have some CPU running software, and the software is controlling what happens here at the end, at the analog line, at the end, at the voltages and the current. And you have a lot of different software algorithms which doing different measurement routines at the line, and which also establishing the performance of the voice part. Then there's another application area for high-speed interfaces. If you want to design especially the equalizer algorithms, then you need a model. The model at one hand at the line, at the driver circuit, to understand the analog behavior. The transmission, of course, is digital, but if you look what happens at the line, then you see there is analog behavior, and you need some fast model to develop the algorithms to equalize a digital behavior. I mentioned before, the sensor circuits, typically in the automotive area, consisting of the sensor element. This is an example of a capacitive pressure sensor. You have some analog signal processing, some analog filtering, some ADC converters. And then usually you have a very, very small processor which does all this whole calibration. And in this case, this was a sensor circuit for airbag system. The circuit is also doing at the processor some preconditioning of the signal, maybe pre-detecting whether this can be a pressure behavior of a crash. And this circuit then later on is embedded in a larger system at the tier 1 level. And there is SystemC AMS very well suited also to provide models which you can exchange with your customers, because you can recompile this model and you can also embed this in other simulators like MATLAB Simulink and can ship it to your customer, which can test this executable specifications in a larger environment. Now this is again an example from the communication area for ADSL and VDSL systems. Their model exists which represents the whole data path and in parallel also the voice path. And this time was very, very interesting to simulate the transient behavior. That means what happens if you have a ringing signal, what happens with the data performance. Is then the algorithms at the data side going into retrain? That means the data transmission is breakdown. And this were possible with the SystemC AMS model. With such models, we achieved the required performance to really simulate this application scenario. This was a case study from the UPMC. They modeled a very, very large wireless system to measure seismic perturbations with a lot of participants. And with SystemC AMS, they were able to handle these large systems. You had at one hand this wireless communication channel. You have different processor models included in this system. Then the interconnect, and then you have, of course, the environment included.